Hello, everyone. Stuxnet, the most infamous cyber-physical system attack, is nearly 15 years old and still relevant. In this talk, we present a comprehensive reconstruction of the Stuxnet attack's impact on the latest version of Siemens S7 PLCs. These PLCs use TLS 1.3 secure communication. Notably, our attack relies on our ability to retrieve the private key from an S7 1500 PLC using a protocol feature provided by Siemens. PLCs are the core of the cyber-physical system. And as we speak, they are evolving. They are increasingly being connected to external networks to get the benefits of the cloud, like machine learning models and digital twins. As a result, the traditional models and architectures we all know are changing, and the attack surface increases. My name is Alon Dankner. I'm a security researcher at the Technion and at No Code Security. And this is a joint work with Professor Eli Biam, Dr. Sarah Bitan, and 3 of our students, Ron Frodenthal, Or Keret, and Nadav Adir, who will be presenting here with me. We're all from the Faculty of Computer Science from the Technion.
Hi, guys. I'm Nadav. I'm a student from the Technion University, software engineering student, and I've worked on this project during my last year of studies.
This is our 4th research on the security of Siemens PLCs, published at the Black Hat Conference. And our studies are even one of the reasons for Siemens to switch to TLS 1.3. So the PLC, or Programmable Logic Controller, forms a bridge between the cyber world and the physical world. And the control program dictates the behavior of the physical industrial process. Now, to spice things up, throughout the talk, we use the Avengers as our actors. So our asset owner is Nick Fury. Captain America is our operator for his great performance in the battlefield. And Iron Man is our engineer for his technical skills. Now, in Siemens' world, we have the HMI, software called WinCC, that allows the operator to monitor the PLC. The engineering station, a software called Step 7, allows the engineer to program the PLC. And both of these software modules are packaged into a single software called TIA Portal. And TIA communicates with the PLC using Siemens S7 protocol. Now, we must have an attacker, and this is obviously Thanos. So today we'll focus on the S7 protocol. S7 is a client-server protocol, where the client is the TIA and the server is the PLC. And it allows the client to send requests or commands to the PLC, like loading a new control program or reading some PLC variable. Now, in the current latest version of the protocol, Siemens use TLS 1.3 for secure communication. But S7 did not always use TLS. In fact, it started as an unencrypted protocol without any cryptography. In 2010, the Stuxnet worm was discovered and drove Siemens to integrate proprietary cryptographic protection to their protocol. In 2019, our team from the Technion published a work called Rogue 7, also in Black Hat USA, where we exploited the lack of client authentication, and hard-coded group key shared between PLCs to implement what we called a rogue engineering station attack, or a rogue client. Now, what's the end of every hard-coded secret? Well, it is being exposed. And 3 years later, researchers from Clarity exposed it. So after the protocol was found to be vulnerable to attacks, Siemens decided to integrate TLS, and this is where we are today. So our goal is to check if the new version of the protocol with TLS is really more secure compared to the previous version. So we want to see if it prevents previous attacks, or maybe is it possible that it opens the system to new attacks? We'll see. So throughout the talk, we'll introduce 6 attacks against S7, and there are 6 infinity stones. So each stone represents an attack. And the goal of Thanos is to collect all 6 infinity stones in order to gain unlimited power and control over the cyber-physical system. So here's our outline. We'll start with some background, and then we move to our attack path, where we look into the TLS encryption. Next, we'll see an attack against the key initialization, and then we'll show how an attacker can retrieve the PLC private key over the network. After that, we'll see how we can use this key to launch a stealth man-in-the-middle attack, and we'll finish with summary and mitigations. So Siemens uses public keys to authenticate the PLCs. In the previous version, all PLCs share the exact same private key. Now, in the current version, PLCs have unique keys. The PLC arrives with an initial private and public key pair, and to bind the identity of the PLC to its key, Siemens uses self-signed certificates, and the PLC created by signing its public key with its private key. Now, in the first connection with the TIA, the PLC sends its self-signed certificate, and since it's the first time that the TIA sees the certificate, it alerts the user and asks him whether to trust the certificate. Once the user approves, TIA pins the certificate to the identity of the PLC, and TIA validates that the same certificate is used on each connection with the PLC. So if Thanos decides to send his certificate to the TIA as PLC2, for example, the user gets the pinning alert and hopefully does not approve. So if the customer, for various reasons, chooses not to trust the initial key that the PLC has, you can use a second way where TIA generates the private and public key pair for the PLC and the certificate. Then the TIA sends or provisions the keys and certificates to the PLCs. And TIA can also optionally act as the certificate authority here. Now, the initial provisioning is secured by the initial keys, and Siemens requires that it must be done in a secure environment. And the asset owner is the responsible to replace the initial keys. Now, compared to the first option, where you only need to hit trust in a message box, provisioning keys is much, much more operationally complex. Now, by a show of hands, who here thinks he can do this provisioning without making any mistakes? Wow, didn't expect that. Absolutely no one. OK. So the provisioning process occurs in a request called hardware configuration download. And the configuration is basically the settings of the PLC. So it includes its network configuration, for example, as well as the keys and the certificate. Now let's see how we can look into the TLS encryption. So those of you who are familiar with PLC reversing probably know the S7 Wireshark plugin that parses the S7 messages. But the plugin does not work on encrypted traffic. So to parse the S7, parse the messages, we developed our own proxy. And this is our infrastructure for our research and for the rest of our attacks, just as the glove of Thanos. So our code receives a TLS encrypted message, decrypts and maybe modifies it, then re-encrypts it before sending it to the PLC. And this applies for messages from the PLC to the TI as well. So we used our code to implement a packet sniffer for S7 that creates a pickup file out of the S7 messages and allows us to investigate the protocol using the existing Wireshark plugin. And it's an open source, so you can check it out. So now, Nadav, our Avengers expert, will show us how to retrieve the private key from the PLC.
Listen, they're good movies, OK? So thank you, Alon. Before we get to our first attack, let's first focus on this initial key provisioning. Our first attack will leverage this provisioning to steal the PLC's private key while it's being transmitted to the PLC. By performing this provisioning, the engineer meant to upgrade the system security, much like Iron Man meant to upgrade Earth security when creating Ultron. And in a bit, we'll see how that turned out. So let's have a look under the hood on this configuration download. First, the TIA initiates a TLS 1.3 handshake with the PLC. In response, the PLC sends its initial certificate. Then, after the handshake has completed, the TIA will send the new configuration containing the new certificate and private key, but it's encrypted. Then, the PLC will decrypt the private key and use it on the next session. OK, so using our TLS decryption tool, we found this packet you're seeing right now in Wireshark. This packet is sent from the TIA to the PLC and contains a lot of data. But most importantly, it contains the private key. After doing some reverse engineering, we discovered that in addition to the TLS encryption, the private key is encrypted again using some standard algorithms and a sequence of ephemeral keys. These are temporary keys, meaning that any attacker with a TLS decryption tool and ambitions to steal the private key will still have some work cut out for them. OK, let's break down the encryption process. So Iron Man, our engineer, asks Jarvis, his virtual assistant, to encrypt the private key which he wishes to provision to the PLC. But he asks Jarvis to make it as unintelligibly complex as possible. Jarvis responds that luckily, there's no need to make an effort. He'll just use TIA Portal's existing mechanism. OK, now we're switching to Iron Man's heads-up display. Jarvis opens TIA Portal for him. Then the TIA takes the new certificate and private key, which Iron Man wishes to provision to the PLC, generates a random passphrase, and uses this passphrase to encrypt the private key. OK, we're not done yet. Next, the TIA generates a random RSA key pair and uses this key pair to encrypt the passphrase. OK. Then the TIA takes a user-defined password, hashes it, generates a random salt. From both of them derives a key, uses this key to encrypt the ephemeral private key, takes all of this data, and sends it to the PLC on the configuration download. That was exhausting. OK, so as you can see by Iron Man's heads-up display meter, this is a confusion meter, he is pretty confused right now. And so are we. but all you really need to remember is that the security of the encryption of the private key all relies on this one password, a user-defined password. Oh, and by the way, this password is a null string by default. Yeah, if the user does not define a password, it just automatically sets it to a null string. OK, so when the engineer creates a new TIA project, he is prompted by this window that asks him if he wants to set up a password. It's not mandatory, though. If he does set up a password, he is enforced with a complexity policy to prevent dictionary attacks. OK, after the user configured this password, he must share it with the PLC, hopefully securely. Well, this password is sent to the PLC on the first configuration download without any additional encryption, meaning that any attacker with a TLS decryption tool can decrypt the TLS and see the password as plain text and can steal it. OK, so now that we've learned all of this, we can piece together our first possible attack. In this attack, the attacker can decrypt and modify all communications between the TIA and the PLC. First, the attacker will act as a man in the middle and intercept the password and private key while they're being transmitted to the PLC. He will take this password and decrypt with it the private key and save it. Then he will let all other packets pass through. And this all happens without any suspicions. This is because on the first connection, no certificate is pinned yet. So the TIA must trust Thanos' certificate. This attack is a brand new attack, since never before did the TIA transmit a private key to the PLC. OK, we saw a very powerful attack right now. But it's not perfect, since not always will the attacker be present when the key is provisioned to the PLC. So the attacker must find another opportunity. In this part, we'll present an attack with the ability to retrieve the private key directly from the PLC deployed on the production floor. But first, we need to look at this other attack first. This attack is the rogue client attack. It allows the attacker to manipulate the operation of the PLC. All we did is we implemented a simple Python script using OpenSSL that impersonates a legitimate TIA. Since client authentication is not enforced, the PLC will accept this connection by our impersonation and do as the attacker commands. The attacker can command the PLC to start or stop or change its configuration. OK, now we can use this rogue client attack for our big attack. With this attack, the attacker can decrypt and modify all the network traffic, but at any time, even if the user never generated new keys for the PLC, or if the attacker missed the initial key provisioning process altogether. OK, here's what the attacker does. The attacker uses the rogue client to send an upload configuration request to the PLC. Then the PLC responds by sending its configuration that miraculously contains the private key. The attacker should have just asked for $1 million instead. The attacker takes the password, or just a null string if it's not defined, and decrypts the private key. Once the attacker has the private key in his possession, he can use it to decrypt all the PLC's network traffic at any time. OK, we've seen multiple attacks. Let's look at the difference between attack number 1 and attack number 3, which both steal the PLC's private key. Well, compared to attack number 1, attack 3 can be performed at any time. It doesn't have to be in the initial provisioning. Attack 3 only needs network access to the PLC, opposed to the initial key provisioning attack, which needs access both to the PLC and the TIA, since it acts as a man in the middle. Both attacks can be performed when the user has not defined a password, since in that case it is a null string. And if the user has defined a password, well, attack number 3 needs to get it, either via a leak or attack number 1, which steals the password. OK, great. Now we'll move to our next attacks. On to you, Alon.
Thank you, Nadav. So now we have in hand 2 independent ways to fetch the private key of the PLC. Now let's move on to our stealth man in the middle. And we split this part to 3 attacks. Going back a little bit, let's see how our rogue client can inject a malicious control program to the PLC. So during the program transmission, the program passes in an encrypted form from the TIA to the PLC. And what we'll see here is a highly simplified abstraction. We removed here layers of obscurity. So to encrypt the program, TIA generates a random seed and uses it to derive an AES key for the program encryption. Then TIA takes the seed and encrypts it under a hard-coded key that is shared between PLC models. During transmission, TIA takes the encrypted seed and the encrypted program and sends them both to the PLC. And this scheme is vulnerable to replay attack, since a program sent to one PLC will be accepted by a different PLC. So in attack number 4, the attacker creates a malicious control program in his own lab with his own PLC, and then he can use a rogue client to load it to any PLC in the world, whether it is in New York, Tokyo, or even New Asgard. And it exploits the fact that the program is independent of the destination PLC due to the shared keys. And even the protocol itself tells you it is a bad idea. And this is real magic from the program encryption in the protocol. So now the victim PLC runs a malicious control program. Let's see now how an attacker can hide it. So attack number 4 is rogue PLC. In this attack, the attacker impersonates the PLC and tricks the TIA into thinking it is the legitimate PLC. Now, this allows the attacker to fake status messages sent to the TIA. Now, since the attacker uses the actual keys and certificate of the real PLC in the handshake, TIA does not show the warning message because it sees the certificate it expects to see. So this is how the attacker bypasses the certificate pinning mechanism. And rogue PLC is a new attack that was not applicable on the previous protocol version. So here's our 6th and final attack. This attack, the attacker recreates the impact of Stuxnet on the latest version of S7. So the PLC already runs a malicious control program, and the attacker causes damage to production. Now, at the same time, when the operators ask the PLC, what on earth is going on here, the attacker, a man in the middle, manipulates the PLC responses to present a false but legitimate state of the process that TIA presents to the users. So what's going on here? This means that on one side, the attacker deceives the operators, but on the other side, the attacker creates complete chaos in production. Now, we see here a full man-in-the-middle attack, where the attacker receives an encrypted TLS message, decrypts and modifies it, then re-encrypts it before forwarding it to its destination. As before, there is no warning message on the TIA, and the attacker can change anything inside the S7 messages. So here's a summary of our attacks. All our new attacks exploit the fact that Siemens protocol transmits private keys over the network, and their protection is not as strong as one might think. So given that we have 4 neoattacks, it is clear that the security of the S7 protocol is essentially not improved and even degraded. So now let's see our demo.
Thank you. So let's get to the moment you've all been waiting for, a demonstration. So what you're seeing before you right now are 3 windows. The first is the engineer Iron Man's window. He has the TIA portal open. The next is Thanos, our attacker. His window is on our proprietary attack tool named Spark, or thematic proxy attack using retrieves key. And the final window is our PLC cam showing the PLC status on the production floor. As you can see, an Iron Man figurine sits atop it, since Iron Man's code is currently inside the PLC. OK, let's start. So first off, Iron Man tries to start the PLC. No attack is being done yet, so he speaks directly with the PLC. And he has started the PLC code, and his code turns on one singular LED, as you can see, an LED. Now Thanos wants to attack this PLC. He wants to inject his own code into the PLC. So he will use our rogue client attack to do a program download request with his own code. Now we're seeing the packets flying from Thanos' window to the PLC. This is a TIA impersonation attack. And
I hope they remember you.
wow. OK, so Thanos has completely changed the code. Demo over. We can go home. OK, not really. So Iron Man in his TIA portal can monitor the PLC's activity. It's what he's doing right now. He is going to the watch table, hitting the button Monitor All, and seeing the current PLC status. This is quite suspicious. He's expecting to see one LED on, and he's seeing all of these LEDs turning on. And he will see this and be suspicious. So Thanos has to do something cleverer. He needs to do a man-in-the-middle attack. So right now, Thanos is starting his man-in-the-middle attack, and all packets that Iron Man will transmit to the PLC will flow through him. This is a simple man-in-the-middle. Great. Now the man-in-the-middle is up and running. Now when Iron Man tries to start the PLC, all the packets will flow through Thanos, but wait. This warning is issued in the TIA portal. This is quite suspicious. It tells Iron Man that the certificate he just received in the TLS handshake is not the PLC's, rather it's an attacker's certificate. So a smart engineer like Iron Man will promptly abort this connection. Aborted. OK, Thanos needs to get even better. He needs to use our PLC private key retrieval attack. He will use our rogue client again to extract the key directly from the PLC by transmitting an upload configuration request, as we saw earlier. Again, this is a TIA impersonation. No client authentication is enforced, so he can do this. He gets the configuration and decrypts it using a null string, since it's by default a null string. And here before you, you can see the PLC's current certificate and private key. This is decrypted. So now he will be using this in the next connection. So now when Iron Man tries to stop the PLC, Thanos uses the correct certificate and no warning is issued.
You could not live with your own failure.
Wow. OK, no warning. This is us. We added this window. So now, what happens when Iron Man monitors the PLC activity? So again, Iron Man hits Go Online, goes to the watch table window. But this time, Thanos meddles with the packets that the PLC televises and changes its status to a forged status, a status that Iron Man is expecting to see one singular LED. Now our man is hitting monitor all, and you can see the differences between what's.
Reality can be whatever I want.
Yeah, reality really can be whatever you want. It's a differences: PLC Thanos code, TIA portal, forged status. Awesome. So now let's get to our second demonstration. In this demonstration, we will show you how Thanos can steal the password while it's being provisioned. So now, our man opens a new tier project, and this time he will set up the password instead of it being a null string. He needs to enter it twice. Great. Now he will go forward with creating the project. We are fast forwarding this process. And now he's entering his certificate manager in the TIA portal, which shows us the new certificate that has been generated with the private key encrypted by the password. Now our man is trying to download the configuration. Thanos has not attacked anything yet, so this is regular transmission from the TIA to the PLC. And we're showing you this because we want to show you that he gets this warning. This warning, there's no attack being made right now. So this warning is totally regular, and it happens since no certificate is pinned yet. Our man must trust this if he wants to provision his own password. So now we have activated Thanos' man in the middle. And this time, when our man downloads his configuration, it flows through Thanos' man in the middle. Now, what happens is before our man provisions the password, he needs to enter it one last time. OK, yeah, so what you're seeing now is the same warning we saw before, so it won't be suspicious. Exact same warning when there's no attack being made, right? So again, man in the middle, same warning, not suspicious. Now, our man will enter his password one last time before provisioning it. There it is. He's typing it in his TIA portal and sending it to the PLC. Now, Thanos is intercepting these packets, decrypting the TLS, and will steal the password. If we go to Thanos' logs from his attack tool, we can search for the extraction of the password, and we can see our man password is I love you 3000. Awesome. So we just saw two powerful attacks in the demonstration that Thanos can do with a snap of his finger. On to you, Alon.
Thank you. So as the demo clearly shows, using the combination of the 6 attacks, Thanos can completely take over any cyber-physical system while hiding its malicious activity. So next, let's see how we can mitigate these attacks. And this is kind of a good news, bad news situation. The good news is that all these attacks can be mitigated using Siemens mechanisms. All you have to do is to use passwords. So you'll need to set the PLC configuration password. You'll need to set the CPU access protection password that restricts access to certain privileged operations on the PLC. If you want to use the TIA as the certificate authority, you'll also define a password for a user in the TIA. And if you want to protect your control program, you'll use know-how protection password. And all passwords must be strong. Passwords must be unique per PLC. And this is the bad news. Large organizations typically have many users stations, and PLCs. Managing this amount of passwords is probably a nightmare. And this is a pain in Nick Fury's asset. So the typical solution is to either totally disable passwords or to define the same password for all PLCs, which is also bad. Now, it's not enough to configure the passwords. Even if you did, now you have to protect them. You'll need to protect them from leakages, and you'll need to protect them from password stealers out in the wild. And you also need to protect them from post-its. Now, we also like to point out that certificates signed by trusted certificate authority won't help you if the private key is exposed. So we disclosed our findings to Siemens, and Siemens is aware that when the configuration password is not set, extracting the private key of the PLC is possible. Siemens recommends the customers to first perform the initial provisioning in a secure and hardened and isolated environment. And you remember that we don't need to catch the initial provisioning to attack the system, right? And second, Siemens recommends to use passwords, passwords, and password. So when the world goes to the direction of passwordless, we see here the opposite direction. And basically, the burden of security is rolled to the customers like a hot potato. Now, if we talk about the protocol design, there are 4 things we can do. First, the protocol must provide mutual authentication. This means that the client authenticates the server, and the server authenticates the client. In TLS, this could be achieved by client certificates. Second, the PLC must never send out its private key. It's simply too valuable, and without it, we don't have security. Third, self-signed certificates should be avoided for initialization. It is more secure to use vendor certificates. In fact, some PLC models already use them. Our PLC model does not use them, though. And last but not least, it is a bad practice to send a key with its ciphertext. It is more secure to use key exchange protocol. And we saw 2 examples for it in the program encryption and in the initialization, where the private key is sent along with the password that protects it. Now, we offer a new scalable authentication and authorization protocol with many advantages that does not require to manage this amount of different passwords. And you should have a look at our paper. The details are in the slide. So I'd like to end with a message. So whether you choose to use TLS or IPsec or certificate authorities, demand secure products. Demand secure products. You are the asset owner, and you are responsible that nothing explodes on your site. Thank you very much, guys, for joining us. I hope you enjoyed it, and we'll stick around for some Q&A in the wrap room. Thank you.